Okay, Assalamualaikum. And how are you doing, sir? Right now, we are hope that you are doing good at the moment. So today we are from the group 2 are going to present to you about the task given to us, which is application of fluid mechanics land wind turbine. So in the group 2, this is the list of members in our group. First one, Derek Ng. Second, me, myself, Muhammad Shamir Azuddin bin Muhammad Nazris. The third one, Alif Razik. The fourth one, Fatih Najira. And the last one, which is Malaysia or Sabrina. Let's we move on to the next slide, which I can explain to you about the abstract. Like what just appear in the screen right now. This is the abstract. So generally, wind turbine is something that convert the wind energy to the electrical energy. And this kind of technology also called as a renewable energy since it's just use the natural from the environments, the natural sources from the environments. So this kind of technology can be installed in most singles and wind farm as a group of wind turbine, which can be either connected to main network or produce electricity independently. This kind of technology also important because it holds immense potential in supplying electricity across the world. Since it is only use wind energy as a source to generate electricity which is free. So wind energy is a home grounds and local landowner can operate single turbines or cluster of turbines. This technology is considered as a green technology because it is not cause exceed range or contribute to the global climate change since it's not emit contaminant into lakes and stream and not even produce hazardous airborne pollutant. So this technology so-called the green technology because it's not cause the exit rate since we know that the sources to generate electricity from this turbine is only use the wind energy. So it can be installed nearby the river, nearby the lakes because it's not going to make pollutions around the river or the lakes. Most other sources that contribute to produce electricity like natural gas, fossil fuel and coal produce greenhouse gases, whereas wind energy produce none of these pollutions. So that's the abstract. Let's move on to the introductions. So as we can see in these introductions, 1,000 years ago, people used wind energy to propel boats along the river or sea. New ways to use wind energy eventually spread around the world, like in 11th century, people in the Middle East were using wind pumps and windmills extensively for food productions. Now in the modern era, wind energy is using as a fluid sources to generate electricity at wind turbine, and wind turbine technology is the most established and effective renewable energy source as well as being efficient at contributing to sustainable development SDG. Wind turbines have three basic parts. The first one, the tower. The second one, the blade. And the third one is the generator. So these three parts is work together to convert energy from the wind into the electrical energy. So the turbines will catch the wind energy with their propeller, the fronts of the turbines. The propeller is just like the blades. And when the wind blows a pocket of low pressure air, it's going to form one side of the blade. Then the low pressure on air pockets to pull the blade toward it and make the rotor to turn. This is what we call lift forces that explain in Bernoulli principles or the Bernoulli effects, where it tells us the faster moving air has lower pressure. This technology is functioned to generate electricity using the aerodynamic forces from the rotor blade, which work like an airplane wing or helicopter rotor blade. So that is the reason why right now we can see the developer make the propeller of the wind turbine which the aerodynamic shapes to make it have a more forces to rotor or to turn the blade or the propeller. So the wind turbine can operate in various speed of wind from very light to very strong wind speed. The average of electricity generated is around 80% of the time, but not always at full capacity. In really high wind speed, they shut down to prevent damage happen. So this is the precautions to use the wind turbines. The infrastructure required for onshore wind power significantly less expensive compared to solar and nuclear power sources. So this is the reason why the wind turbine is the most established technology, because it has a cheaper cost to install rather than solar and nuclear power sources. The cabling voltage loss is reduced when there is less space between the turbines, and the consumer have less impact on the surrounding areas because toxins are not released and contributed to very little impact to wildlife. So that's all from me. We move to our next member, which is Derek that are going to present to user about this kind of available design in the world. So yeah, take it, Derek. That's all from me. Assalamualaikum warahmatullahi wabarakatuh.
Hello, I'm 2200927 Derek Ng. Now I'm going to present to you the available design of onshore wind turbine in the world. So there are two types of wind turbine. The first one will be horizontal axis wind turbine. The second one will be vertical axis wind turbine. So the horizontal axis wind turbine is common and well known, and the blade spin perpendicular in one direction. Usually comes with 3 blades. It have to be placed in the greatest wind area, such as flat ground, mountain gap, mountain, or high ground seashore. And this horizontal axis wind turbine produce high voltage of electricity. Then the second one will be vertical axis wind turbine, which is less popular. The blade also spin in perpendicular, but in all direction. We have 2 horizontal blades, looks like an egg shape, then generate electricity in low wind speed and usually used in urban environment. And this vertical axis produce low electricity. Okay, so next will be the working principle of the wind turbine by parts. So the first one will be the rotor blades. The rotor blades have the airfoil shape, so the wind will flows through these rotor blades and produce a different pressure in the front and the back. So therefore, the lift and drag happens on the blade to rotate the blade and the generator. So the Bernoulli equations can be used in these rotor blades with a high speed of air and with low pressure. So the next one will be the gearbox, which is a step up because the blade turns slow and the gearbox rotates the generator in high speed. Then the naphthalene, which is the casing for the wind turbine, and the generator, which converts the mechanical power into electricity. Power cable is connected the cable from the turbine to transformer and switch yard. So the tower is the structure of the wind turbine. Transformer here is using step-up transformer because the electricity from the generator will be stepped up and increase the voltage to the switch yard. So the switch yard is where they distribute the power to the area. Wind turbine that has been used on today's technology lah. Then the first one is Vestas. Vestas is the tallest wind turbine, comes with 4.2 megawatts. And General Electric Renewable Energy, we produce 4.8 megawatts to 6.3 megawatts, which is the largest power output wind turbine. Then follow up with the Goldwind Smart PMDD, then Siemens Gamesa, and Eneron. Okay, then these are the country that use the wind electricity, wind powered. Okay, so the installed wind electricity capacity are in gigawatts. So These are the country. The first one is China, US, Germany, follow India, and so on. Okay. And this is the wind farm, which is the wind power plant. So the wind turbines powers the wind, okay, and generate electricity, go through the transformer, step-up transformer, switch yard, and transmission lane, which is the switch yard, to distribute to the area. That's all from me. Thank you very much.
Theory of wind turbine. A simple model may be used to determine the power from an ideal turbine rotor, the thrust of the wind on the ideal rotor, and the effect of the rotor operation on the local wind field. The analysis assumes a control volume in which the boundaries are the surface of a stream tube and two cross-sections of stream tube. So this is the diagram that we want to use for the calculation of momentum theory. Only the stream tube's ends experience flow. The turbine is symbolized by a uniform actuated disc that causes a pressure discontinuity in the air stream tube that is passing through it. No specific kind of wind turbine is constrained by this strategy. The following assumptions are used in the analysis are: no frictional drag, a non-rotating wake, an infinite numbers of blades, homogeneous incompressible steady-state flow, uniform thrust over the disc or rotor area, and the static pressure far upstream and far downstream of the rotor is equal to the undisturbed ambient static pressure. The disc model with no wake rotation. This is the diagram. The formula includes conservation of linear momentum, where T is the uniform thrust exerted on the disc rotor, which can be expressed as a function of pressure change as follows. T is positive, so the velocity behind the rotor U4 is less than the free stream velocity U1. No work is done on either side of the turbine rotor. Thus, the Bernoulli equation can be used in the two control volumes on either side of the actuator disc. So from Bernoulli equation, energy conserved. For the stream tube upstream of this, we have this equation, and stream tube downstream of this, you can use this formula. It is assumed that the far upstream and far downstream pressures are equal, P1 equal P4, and that the velocity across the disc remains the same, U2 equal to U3. Connect the two equations above and specify the axial induction factor A as A equal to U1 minus U2 over U1. Then we get T equal to half times mass flow rate power of 2 times 4A times 1 minus A. The thrust times the disc velocity is how a turbine calculates its power output. Hence, P equal and T equal to this. Typically, the power and thrust coefficient of a wind turbine rotor serve to define its performance. So this is the formula of power and thrust coefficient. Take note that when a power is being absorbed, wind velocity at the rotor plane is always lower than the free stream velocity. This model makes no assumption about wheel rotation, therefore there is no kinetic energy loss in the whirling wake. Calculations are not required for the blade geometry. One may easily calculate the thrust and power production if the axial inductor factor of the rotor is established. Maximum power is produced by the ideal turbine. The axial induction factor A for the ideal turbine can be calculated to be 1 over 3 after some adjustment. It is impossible to capture more than around 60% of the kinetic energy in the wind, even with the finest rotor design. Next is actuated disc model with wake rotation. In reality, the generation of rotational kinetic energy in the wake results in less energy extraction by the rotor than would be expected without wake rotation. In general, the extra kinetic energy in the wind turbine wake will be higher if the generated torque is higher. Thus, as will be shown here, slow-running wind turbines with a low rotational speed and a high torque experience more wake rotation losses than high-speed wind machines with low torque. So this is the diagram of actuator this model with wake rotation, where capital U is undisturbed wind velocity, A is induction factor, area of annular stream tube of radius r and thickness dr is 2 pi r dr. The distribution of the thrust is uniform around the circumference. So this is the formula of conservation of linear momentum and conservation of angular momentum that we use in this question. So next, assuming angular velocity omega imparted to flow in small compared to angular velocity of the rotor, where pressure in far wake equal to pressure in free stream. The pressure, wake rotation, induction factors are all assumed to be a function of radial position r. Using a CV that moves with angular velocity the energy equations can be applied at sections before and after the blades to derive the pressure difference across them. Across the flow disk, the angular velocity of the air relative to the blade increases from to plus omega, whilst the axial component of the velocity remains constant. So from Bernoulli equation, energy conserved, we obtain this equation. Then the resulting thrust on n annular elements dt is this. The angular induction factor A prime ought to be defined as A prime equal to omega over 2 ohm. Note that when wake rotation is included in the analysis, the induced velocity at the rotor consists of not only the axial component U, A, but also a component in the rotor plane, R A prime. So the expression of thrust become this equation. When the thrust on an annular element is calculated using the Bernoulli's equation and the conservation of linear momentum, the result is this, where lambda r equal to lambda r over capital R and lambda equal to r capital over U. To achieve the maximum power production from an ideal turbine, we can use A prime equal to 1 minus 3A over 4A minus 1. Lambda r is the local speed ratio. Take note that the calculations are still not necessary for the geometry of the blades. Second, one can find A and A prime in each part if it is assumed that the turbine is perfect and producing its full power. Third, by integrating along the blade span wise, the entire thrust and rotor torque can be calculated once A and A prime have been founded. So next is lift and drag forces. Airflow over an airfoil produces a distribution of force over the airfoil surface. For lift force, it is defined to be perpendicular to the direction of the oncoming airflow. The lift force is a consequence of the unequal pressure on the upper and lower airfoil surface. Drag force, defined to be parallel to the direction of oncoming airflow. The drag force is due both to viscous friction forces at the surface of the airfoil and to unequal pressure on the airfoil surface facing toward and away from the oncoming flow. So this is the formula of lift force and drag force. Note that CL and CD vary with cross-section. Element theory. The forces on the blades of a wind turbine can also be expressed as a function of CL, CD, and alpha. For this analysis, the blade is assumed to be divided into n sections or elements. Assumption: there is no aerodynamic interaction between elements. The forces on the blades are determined solely by the lift and drag characteristics of the airfoil shape of the blades. So this is the diagram of blade element. The blade element. We may utilize this geometry to compute the induction factors that link thrust and rotor torque. Next is relative velocity. In a horizontal direction, wind speed at the rotor blade equals to u1 minus a. In addition, as the angular velocity of the rotor is in the opposite direction, the wind rotates with an angular velocity of omega over 2, or it is equal to a prime. So this is the diagram of relative velocity. Next is blade geometry. From blade geometry, one simply obtains the following relations. This is the diagram of blade section geometry. This formula shows the following section relationship. The tangential, the torque caused by the tangential force acting at a distance of r from the center is equal to the sum of the normal forces acting on the section. So if rotor has B blades, total normal force on section at distance r from center is dFn, and differential torque due to tangential force operation at a distance r from the center is given by dq. Since the forces and moments derived from momentum theory, the model and blade element theory must be equal. So this is the formula when it is moment theory equal to blade element theory. This equation and the empirical C versus curve can be used to find C and at each section. CL. Both parameters are known. A and A prime at the section can be determined from this, and there is iterative solution for A and A prime. This approach may result in a lack of convergence to a solution in the case of turbulent weights. Loss factor. Due to the rotor having a finite number of blades, the tip loss factor enables for the velocities and forces to not be circumferentially uniform. It is possible to express the Prandtl tip loss factor as F. This is the formula of tip loss factor.
The discussion part, which is the benefits of wind turbine. Wind power is a clean and renewable energy source. Wind turbines harness energy from the wind using mechanical power to spin generator and create electricity. Not only is wind an abundant and exhaustible resource, but it also provides electricity without burning any fuel or polluting the air. Next is wind power is cost effective. Land-based utility scale wind turbines provide one of the lowest price energy sources available today. Besides that, wind turbine works in different settings. Wind energy generation fits well in agricultural and multi-use working landscapes. Wind energy is easily integrated in rural or remote areas.
onto turbulent flow towards, near, and behind a wind turbine. Wind energy conversion and turbulence. A wind energy conversion system extracts energy from the turbulent wind and while doing so creates extra turbulence. The flow towards a wind turbine. The flow towards a wind turbine is essentially turbulent, with wind speed variation originating from production of turbulent kinetic energy due to surface roughness in combination with production or destruction of turbulent kinetic energy due to atmospheric stability. Next is the flow near a wind turbine. Upon approaching a wind turbine, the wind speed decreases and the turbulence increases in anticipation of the flow disturbing an energy extracting object. The flow near a wind turbine is modeled by using a rotor disc which contains the rotor blades. Flow through the disc traditionally is modeled homogeneously under the assumption that the wind speed and the turbulence do not depend on the position in the rotor disc. Although it is not unusual to include some inhomogeneity in the form of a horizontal or vertical wind gradient in order to model wind shear respectively, your misalignment. The turbulence in a point in the rotor disc is modeled on basis of a spectrum. Last but not least is the flow behind a wind turbine. Here we can see two figures which shows the flow behind a wind turbine. The flow behind a wind turbine is subdivided in three regions, each requiring distinct modeling approaches. This is shown in Figure 1 and Figure 2. In the near wake, the flow is dominated by the velocity deficit due to the energy extraction and the vortices created at the tip of the rotor blades, resulting in a wind speed deficit and extra turbulence. On the aeroflow structure essentially depends on the aerodynamics of the rotor blades. On basis of solutions, flow problem and empirical information, the resulting flow is assumed to have a top hat shaped wind speed profile and edge concentrated turbulence. In the intermediate wake, the tip vortices gradually lose identity and the undisturbed flow mixes with the core flow. As a result, the wind speed deficit and the extra turbulence begin to decay. Efficiency wind turbine efficiency. Efficiency of wind turbine equals to network over Q in equals to P out over P in. Usually, efficiency is defined as the ratio between two terms which are the amount of network to be input, energy to be devised. Efficiency can be alternatively defined as the ratio between the derived power and the rate of energy flowing to the system. The power coefficient of the Bear turbine was considered under the assumption of frictional losses. In this case, the power coefficient can also be identified as the efficiency of the wind turbine. Next, we move on to the effect of turbulence on electricity production and mechanical loading. For this topic, we can subcategorize into two categories. The first is individual wind turbine, and the second is cluster of wind turbine. First, we move on to individual wind turbine. The wind exerts forces on the rotor blade of a wind turbine when rotating. The in-plane components of the aerodynamic force on the rotor blade causes torque about the rotor axis. Similarly, the out-of-plane components cause thrust on the rotor. Turbulence now leads to time variation in the rotor shaft, torque, and the rotor thrust. The aerodynamic power is the product of the rotor shaft torque and the rotor speed. Turbulence, therefore, gives rise to the variation in the power and consequently the electricity production. In fact, turbulence is believed to be essential in assessing energy yield. Last, the mechanical loading of the component of a wind turbine, like the blades or the shaft, originate from the aerodynamic force on the rotor blade. Turbulence, therefore, causes variation in the mechanical loading. In other words, it causes fatigue loading. To date, fatigue loading is considered the primary factor which determines the lifetime of a wind turbine, and several methods for designing lifetime exist. Understanding and characterizing turbulence before and behind wind turbine to be essential here. Next, we move on to a cluster of wind turbines. In a cluster of wind turbines, the flow towards a given wind turbine is affected by the velocity deficit and the extra turbulence due to any upstream wind turbine. Such a cluster usually is referred to as a wind farm. In general, this interaction leads to a complex structure of the flow in and behind the wind farm. For example, depending on the wind direction and the layout of the wind farm, regions with multiple velocity wakes and multiple turbulence wakes may be identified. In this section of the paper, the focus is on the relatively simple case where the wind direction is parallel to a row of wind turbines. The limit situation of the upstream wind speed and the ambient turbulence only is reached after the most downstream turbine of a row of wind turbines. The limit situation of the upstream wind speed and the ambient turbulence only is reached after the most downstream turbine of a row of wind turbines. The limit situation of the stream wind speed and the ambient turbulence only is reached after the most downstream turbine of row of wind turbines. That is all for our group.